Hello all, welcome to my channel. Let's start with the behavior of perfect gas and kinetic theory. This is under class 11th. So the first topic under this is the introduction of gases. So as you know that in gases the intermolecular forces are very weak and its molecule may fly apart in all directions. So we have characterized the gases on three bases. One is on the shape, size and vessel. So in this case, as you know that the gases doesn't have a specific shape and size. There is no specific shape or size, and we can easily obtain them in a vessel of any kind of shape or size. Like here I have drawn three shapes. One is a bigger rectangle, another is a square, and another is a circle one. So here we have three types. So if we have three types, it can take any shape. Any means any. The next one, it says that it expands indefinitely and uniformly to fill the available space. Whatever space they have in their surroundings, they will try to fill that space. It can't be a empty space in that. So they try to actually find a space and expand. The third one, it exerts pressure on surrounding. As you might have learned in class 9, that gas exerts pressure on the walls of the beaker. So it is same as you learned in the class 9. It says it exerts pressure on surrounding. So they have lots of kinetic energy. So they try to escape that place, but end up they end up meeting the walls of the beaker. So that's what it says, that it exerts pressure on surroundings. So this is about introduction of the gases. So the next thing is we need to learn about various gases like the ideal gases or the perfect gases. So in that we need to learn about the pressure, what pressure they apply on the gases. So let's move on to that. Let's start with the second one, assumptions of kinetic theory of gases. So in this, it was given by Clausius. It was first stated by Clausius, then it was modified later on. Now, the first one was stated as, it says that a gas consists of very large number of molecules, which is equivalent to 10 raised to power 23, and which is equivalent to Avogadro number. It was stated that gas consists of very large number of molecules in it, and they are equivalent to 10 raised to power 23 and equivalent to Avogadro number. And later on it was said that the molecules in it are perfectly elastic spheres. And then it was stated that suppose we have a hydrogen gas in it. Now the molecules must be present here, and molecules within hydrogen gas in a box will all be same. Now let us suppose a gas chamber of oxygen. Now the molecules within oxygen will be same, but if you compare it with hydrogen and oxygen gas, they will be different. They have different properties. Now, so what we learned here is that the gas consists of very large number of molecules, which is equivalent to 10 raised to power 23, which is equivalent to Avogadro number. Then it was stated that they are identical in all respects for a given gas and are different for different gases. That means within one gas chamber, the molecules present have same properties, but if you compare it with oxygen, they have different properties. So this is what we learned from the first one. Let us move on to the second one. The second one says that molecules of a gas are in a state of random motion. So the molecules within the gas system are in random motion. That means that all molecules have different speeds, different directions, and they obey Newton's law of motion as well. So it was stated that they all move in a random motion, and it was stated that they move in all direction. And they have a speed of about 500 meter per second. This is the average range of one gas molecule present, and they all obey Newton's law of motion. So what we learned from here is that they all are moving in random motion, and they all have different directions with different speed, and they obey Newton's law of motion. The third one says that the size of gas molecule is very small as compared to the distance between them, between two molecules. So suppose that the size is of 2 angstrom and the typical distance between the two gas molecule is about 20 angstrom. So you can see the difference between these two. So therefore it is says that the size of gas molecule is very small as compared to the distance between them. Hence, if I say this, that means that the volume occupied by the molecule is negligible in comparison to the volume of gas. That means volume present of molecules is very less as compared to the volume of gas because of the difference between the size and the difference between the distance of two molecules. So that's the reason the volume of molecules is very less as compared to the volume of gas. Let's move on to the fourth part. So the fourth part says that the molecules do not exert any force of attraction or repulsion on each other except during collision. There is one phenomena that is under molecule of gases is collision. There is no force there is no force of attraction and no force of repulsion between two molecule of gases. But there is one process that is collision. Let's move on to the fifth part. So the fifth part says the collision of molecules within themselves and with the walls of the vessels are perfectly elastic. As we have learned in the fourth one that there are collisions. So in the fifth one it says that they are perfectly elastic. Now what do you mean by perfectly elastic? So perfectly elastic is that when momentum, kinetic energy are conserved, but their velocities change. So what we learned from the fifth one is that whenever molecules collide or molecules collide with the vessels, they collide perfectly elastic. The phenomena is perfectly elastic, and the perfectly elastic means when the momentum and the kinetic energy remains conserved, but the velocities of the different molecules changes. So this is what perfectly elastic means. Let's move on to the sixth part. Sixth part says that there is no concentration of molecules at any point inside the container, that is, molecular density is uniform throughout the gas. That means suppose we have a beaker and in that we have gas molecules present inside them. And the sixth one says that the molecular density of the beaker will be constant. That means if you take any part of the beaker and find the molecular density of it, then it will be same for all the corners or all the parts of the beaker. So this basically means that the molecular density remains constant inside the gas. So this is what sixth is about. Then moving on to this one. So seventh one is that in which it says that a molecule moves along a straight line between two successive collisions, and the average straight distance covered between two successive collisions is called mean free path of all the molecules. So basically means that the molecules move in a straight line. And if they are moving with straight line, that means they have constant speeds. And if they have constant speed, therefore they have successive collision. They are meant to collide if they are moving with a constant speed. And the distance covered by the molecules between two consecutive successive collisions is known as mean free path. So this is about seventh one. Moving on to the eighth one. Eighth one says that the collisions are almost instantaneous. That is, the time of collisions of two molecules is negligible as compared to time interval between two successive collisions. Whenever we talk about instantaneous word, it means that the time of collision of two molecules is very negligible as compared to the time interval between two successive collisions. So therefore we say that the collisions between gas molecules are instantaneous. So this is about assumptions of kinetic theory of gases. The next topic, we need to move on to the next topic, and it is pressure of an ideal